Hi, in this session, we will design a finite state machine project and we will use a PLL to understand the concept of Quartus IP Wizard. These are two different things, and today our primary focus is on Quartus IP Catalog. Quartus Catalog includes many widely used modules, which you can use in your projects for free. Means you do not need to write a VHDL code for these predefined modules. So you can simply select the IP from Quartus based on your project needs, import it, and boom. Now you can use that in your project. This is as simple as that. No VHDL code, nothing. Interesting, right? So let's understand it by one simple example, and we will use it in our today's project as well. So suppose your FPGA board frequency is 50 megahertz and your project requirement is to use 25 megahertz of clock frequency. Then what you will do? Simply you will design a frequency divider, right? But instead that, you can simply import a predefined IP in Quartus Prime, and that IP will do this job for you. And so you do not need to write any VHDL code for this frequency divider. So this is one example. But Quartus Prime supports a wide range of IPs from different categories. For example, Quartus has memory elements like RAM, ROM, etc. Processors, communication protocols like Ethernet interface, audio and video interfaces, etc. Serial communication protocols, error detectors and correctors, filters, signal generator, and this list is really big. So today's task, we will use a PLL IP for frequency division. We will learn how to import it, how to configure it, and how to use it to get our desired requirements. Then we will use that output clock signal to drive a finite state machine, which will be our prototype of a manual traffic light system. Okay? Okay, so let's understand the finite state machine requirements first, and then we will move to the coding part. All right? Okay, so let's assume that you are at this stage 1, and at this time you can see that red LED is on and this yellow LED and this green LED are off. So this is our state 1 configuration. And now when you press this switch 1, so this is our switch 1, then we will move to stage 2. So we will jump to this stage 2. Now at this state, you can see that yellow LED is on and other two LEDs are off. So this is red and this is green. Now if you press this second button, so suppose this is switch 2, and when you press this, then you will jump to this state 3. And at this state 3, you can see that this green LED is on and rest two LEDs are off. Alright. So now when you are at this state 3, and again you press this switch 3, so suppose this is our switch 3, then our finite state machine will jump back to this state 1. Okay, and this will go in a loop. You press this switch, then you will jump from state 1 to state 2. Now you press this switch 2, then you will jump from state 2 state 3, and when you press this switch 3, then you will move from state 3 to back to state 1. Okay, and these are the outputs for each individual state. So this is our design idea. Now let's go back to the Quartus Prime software. Okay, so let's open the Quartus Prime software first. So click on this Windows Start button. Now write Quartus Prime. So this is the Quartus Prime version we are using. So click on it. Now for this task, we will create a new project. So click on this new project wizard. So this is the new project wizard window. Now click on next. We have already gone through to this process multiple times in this session. So this time we will be a little fast. So first we will create a new folder for this new project. Suppose I want to save my project in this folder, and here we have this My Designs folder. I will select this. Now this time I will create a new folder and I will give the name that is IP test. Okay. Now enter and select this folder. Now we will give the name of this project, and suppose the project name is same, that is IP_test or IP test. Now click on next button. Now select this empty project button and then click on next. At this page, you can add any existing VHDL file into your project. But for this project, let's leave this as it is, as we are not going to add any existing file into this project, right? So click on next. Now at this page, we will select the FPGA device that we are going to use in this project, right? So for example, I am going to use a Cyclone 4 device. So I will select this Cyclone 4E from the device family. Now you can use these filters to shorten the list of the FPGA devices. So you can see that all the FPGA devices belongs to Cyclone 4 family, and this is quite a big list. So you need to select the exact FPGA device you are going to use, right? So we can use these filters here to shorten down this FPGA device list. Okay, for example, the package which we are going to use is QFP. So I can select this TQFP package. Now I have the another filter, that is pin count. So I will select this 144 pins. And the next filter is speed grid. So our FPGA is having the speed grid of 8. So I will select this. Now you can see that only 4 FPGA devices are listed here. So I can choose my FPGA device much easier, right? So for example, I have this FPGA and you can read it by name as well. So this is EP4C. So this is Cyclone 4. 4C means Cyclone 4. And in the last, that is C8. So that is 8 speed grid. Okay, so that we have selected here, right? And also you can see that this FPGA device comes with what elements or what features. For example, this FPGA device has total 92 input output ports. So total pin count is 144. That includes VCC, ground, and the power pins for the each bank. So out of this 144, 92 input output pins are available. Okay. Next, you can see the memory bits. So this number is the total number of memory bits you are having in this FPGA device. You also have embedded multipliers, that is 9-bit. So you have 30 in total. Next, you have 2 PLL in this device. And we are going to use 1 PLL for this project. And we will have 10 global clocks in this FPGA device. All right. So after selecting the FPGA device, I will click on next. Now because I'm not doing the simulation in this project, so I will leave this page as it is and I will simply click on next button. And finally, I will click on this finish button. So you can see that our IP test is created here and we have selected Cyclone 4 device and this is your FPGA device, right? Now first I will create a VHDL file. So for this, I will click on this new button. Now I will select the VHDL file from this window and simply click on OK. Now the first thing that I will do that to save this file by giving some reasonable name. So for example, this is vhdl1.vsd because that is automatically created by the Quartus Prime software. So I will go to this file tab and then I will select this save as. Now as usual, I will create a new folder here and I will give it name, that is source. So that is our source file. Now enter. Now I will open this folder and I will save this file as IP test, and that will be our top level module as well for this project. So simply click on this save button. So you can see that the name of this file is updated, that is iptest.vsd. Okay. And now we are using the same code that we have previously designed in this learning series, and that was our FSM project. Okay. So I do already have that VHDL code. So simply I will open this file and I will copy the whole text. And now I will paste it into this VHDL file. Okay. And now let me quickly brief this program so that you can just recall. Although we have already explained this program previously, but still let me give a quick brief to you. So this is our library section. So library IEEE and use IEEE.std_logic_1164.all. Next, we have this entity section. So our entity name is test01. So that is our project name as well. So we need to change this test01 to IP test for this project. So I will copy this, paste this, and paste this here as well. Now remember that your top level module or your project name must match with the entity name here. Okay. So previously that was test01, but our project name is IP test. So that is why I have changed this name to the IP test. Okay. Now this module has 4 ports. So you can see we have these 4 ports here. We have clock. So that is input type and std_logic. We have reset, that is again input and std logic. We have one extra input, that is switch, and this is STD logic vector, and the range is 1 to 3. Means this port having the 3 indexes inside it. Alright. Next we have the LED as an output type, and this is again STD logic vector, and the range will be 1 to 3. Means 3 indexes inside this output. Okay. Now we have this architecture section from here till here. So what we have did here, that these two lines are for the custom data type, because we are going to use a finite state machine in this program. So we have this custom data type that is named as state, and this will have the element of red, yellow and green. Okay. And that is our traffic light. Now once we define the data type, we will create a signal from that data type. Okay. So signal present state, and that is of state data type. Means this present state signal can have these 3 possible values. So that is red, yellow and green. Alright. Next we have started the architecture section, and we have simply created our state process. Now this is the register process block. So we have clock and reset in the sensitivity list. And now first we have given the reset condition. So if reset is high, then our LED output will be 0. Means all the LED outputs are off. Okay. And also we will reset our state or the present state, that will be red for the red signal of our traffic light. Now what will happen at the else if condition, means at the rising edge of the clock, we will use the case statement here. So case present state is, so when this present state is red, LED output will be 100. Means the red LED will on and yellow and green LED will be off. Okay. So for example, the first LED is red, second LED is yellow, and the third LED is green. Alright. Let's mark this comment. And now we have the condition that if the switch 1 is pressed, then our present state will be yellow. So when you press this switch, you will jump to this next state. So that is yellow. Alright. Now at this state, the LED output will be 0, 1, 0. Means the yellow output or the yellow LED will glow and the rest 2 LEDs will off. Alright. And now we have the same condition that if switch 2 is pressed, then we will move to the next state, and the next state will be green. Okay. So when you are at this green state, then the output will be 0, 0, 1. Means this green LED output will be 1 and the rest will be 0. Alright. And when you press this switch 3, then your state will change to red. So this is the very simple finite state machine program. And in the last, we also have this when others condition. So this is same like the reset condition we are having. So we have this LED output that is 0 and the present state will be red. Okay. And in the last, finally, we AND the case with this statement. Then we AND if to terminate this if condition. Then we will AND the process, and finally we will AND the architecture. So this is our very simple finite state machine program. So first we will quickly compile our program to check if this program is having any syntax error or not. Alright. So I will go to this play button and I will click on this to start our compilation process. So this is asking to save our program. So yes, we wanted to save this. Now the compilation of our program is started. So it will take a couple of seconds. So we will wait for the results. And it is done. And the good thing is we do not have any syntax error in this program. Alright. So now this is the time to use the IP catalog in this design. So what we will do, that we have this clock that is 50 megahertz in our board frequency. So this is 50 megahertz. And now suppose we are having the requirement to use a 25 megahertz of a clock frequency to drive this state process. This means that we have to divide this input clock or this board clock frequency by 2, right? So one way is you can simply write a VHDL code to divide your input clock frequency, and for doing this you have to write a complete code for that clock division. But here instead we are writing a VHDL code, we will use a PLL for doing this clock division for us, right? So you can see that we have this IP catalog window here, and if you don't see this window like this, then you can simply open this from the tool tab. So you can see this tool tab here, and here down the section you will see this IP catalog. So simply click on this IP catalog button, and you will get the same window here. Okay, so this we call IP catalog, and inside this IP catalog you are having multiple categories for these IPs. For example, we are having this basic function, so you can expand this as well. So inside this you can see we have arithmetic IPs, we have clocks, PLL and resets. We also have on-chip memory, so you can see that if you wanted to use RAM or ROM, so you can simply directly use them from this catalog window. We do also have shift registers. Apart from this, we have this DSP for digital signal processing. So here we are having this error detection and correction techniques. So you can use them. You are having filters, you are having signal generations. So you can use any of them into your project very easily, right? We do also have the interface protocols, like for audios and videos, we are having these. We also have Ethernet interface. So you can simply open this 1 gig multiple rate Ethernet. We do also have the serial communication like SPI, LPC, etc. Other than this, we also have memory interfaces. We do also have processors. So you can use these NIOS too in your project. You do also have embedded processors. You can also use them. Next, we have peripherals and then university programs for audio and video, clocks, communications, memory, etc. Right? So you can see that this Quartus Prime software already have multiple and different type of IPs for your use, right? But in this program, we are really interested in the clock IPs, right? So we have this clock IPs inside this basic functions category. So simply select this basic functions. Now you will see this clocks, PLL and reset. So simply expand this. Now we are having the PLL category here, and we are going to select this Alt PLL for this program, right? So simply double click on this. Now this type of window that will open. So here it is asking for the folder name or the folder location. So what I suggest to create all the PLLs in the separate folder, and I do generally create a new folder named as IPs. And now I will create another folder for PLL, or you can give some other name like for clock, because in this program we are only going to use one PLL. But if you're designing some bigger project, then you might interested to use more than one PLL in your project. So it's better to differentiate them by folder. Okay, so simply I will create another folder that is PLL, and I will give the name PLL or even clock PLL to this IP. All right, now click on save. Now you can see we have two options, that is VHDL and Verilog. So I will select this VHDL tab, and after this simply click on OK button. And now this is your IP wizard. Now let me quickly adjust the window size here so that you can see everything in one view. Okay, so this is our first page of this IP wizard for this clock PLL. All right. Now at the top left, this is our block diagram for this PLL. Okay, so you can see that the name of this PLL is clock PLL, and we have selected this name for this, right? And now here you can see the FPGA device, so that is Cyclone 4E device. Now this module having the two inputs and two outputs. So the inputs are in clock 0 and asynchronous reset, and the output are C0 for the output clock, and one is locked output to lock this clock PLL. All right. Now if you look here, then it is by default selected 100 megahertz for this module, and we know that is not correct for our board, right? Because our FPGA board is using 50 megahertz of clock frequency. So first we will correct this, and you can see that it is asking here to choose the input clock frequency. So what is the frequency of the input clock, or in clock 0 input? And it is by default selected 100 megahertz. So we'll correct it to 50 megahertz. Okay. Now once you do this, you can also see, so that is updated in the block diagram as well, right? Next thing that is important in this page, that is the speed grade of our device. So now we know that the speed grade is 8 for our FPGA, because the device that we have selected is this, and you can see that in the last that is written C8, means this is having the speed grade of 8. So simply select our speed grade, so that is 8. Now leave everything here and just simply click on next button. And now in this page, you can control your input and output ports. So for example, these are the optional inputs here. And in this block diagram, you can see we have two inputs. That is clock, so that is mandatory. But this asynchronous reset is the optional signal or the optional port for this PLL, right? But it is always better to use the reset in your projects, right? So I will leave this input port as it is. But if you do not want to use this reset signal, you can just simply untick this and you can see that input port will be gone from the port diagram as well. So now I will take it back because I wanted to use this reset port in our project. Similarly, we have optional output ports and you can see we have this logged output, and for this project, we do not need to use this output logged port. So I will simply untick this from here and you can see that is gone from this block diagram as well. All right. So now simply click on next button and I will leave these settings as it is. So simply click on next. Now this is the page for clock switchover. So in your project, in case you are using more than one clock frequencies as an input, so in that case, you can use this clock switchover. So once you tick on this, then you will have the extra clock frequency in the input port and you can select whatever the frequency you are having on that second clock input. And also you will also have one extra input port for clock switching, and you can use this to either select the clock 0 or clock 1 dynamically in your program or dynamically in your project. All right. But in our FPGA board, we only have one clock frequency. So I do not need to use this clock switchover. All right. So I simply untick this option from here and then click on next. Now this is asking for the dynamic configuration. Now we know that we are having the board frequency of 50 megahertz and we wanted to get our output as 25 megahertz. So this is very strict that we know the input and we know the output. All right. So we do not need to use any dynamic configuration in our program or in our project. All right. So I will leave all the settings as it is and simply click on next button. Now this is an important page because in this page we will configure our output clock frequency. All right. So we will have a couple of options to choose our requested output. So for example, I can use this multiplication factor or the division factor. Now because our input frequency is 50 megahertz and the output frequency is 25 megahertz. So we know that the output frequency is the division of 2 of the input frequency, right? So you can use this clock division factor and that will be 2 for our requirements, right? So you can see that the actual setting will be 25 megahertz. So that is one way of selecting your output frequency, but I will prefer this second way, and that is enter output clock frequency. So I will select this option and here I just need to give that what frequency we wanted to get at the output. All right. So for example, in our case, we wanted to get 25 megahertz at the output port, right? So I will simply write that 25 megahertz that we want to get at the output. And once you do this, your Quartus Prime software will automatically adjust the multiplication factor or the division factor according to your configurations from the input or from the output. All right. Another thing that you can select in this IP catalog or this PLL module, that you can control this clock phase shift for your output clock frequency. So you will have multiple options to select this. So you can select this from the degree perspective or from the nanosecond perspective or picosecond perspective. So Quartus Prime is quite flexible on the requirements, and that is why this PLL can be used in many different ways and can cater multiple of your requirements. For example, you can also control the duty cycle of your output clock frequency. So by default, that is 50%, means 50% time it will be at logical high and 50% time of one clock cycle at state 0. All right. And based on your requirement, you can adjust this duty cycle as well. But for our project, 50% duty cycle is completely fine. So I will not touch this setting at the moment. Now, once you are happy with the configuration of your output port, you can simply click on next. Now, if you notice, that is the same page as we have in the last page, right? Because this PLL allows you to select multiple output ports based on your project needs. And you can select up to 5 clock outputs. So you can see these tabs here. So that start from C0 and goes up to C4. So if you want to have one another clock output of, for example, 10 megahertz, so you can simply tick this box and now you can select the output frequency. For example, this second clock output is 10 megahertz. So you can see that in the block diagram, two clock outputs, that is C0 and C1. So C0 is configured for 25 megahertz output and C1 is configured for 10 megahertz output. And you can see the division factor is 5 because the input frequency is 50 megahertz and we wanted to get a 10 megahertz from that. So once you are happy with the second clock, you can click on next and it will ask for the third clock frequency. So again, if you want, you can use this to generate the third clock output. And for example, this time you wanted to get 100 megahertz as an output clock frequency. So once you select this, you can see that now the configuration is set that the clock multiplication factor by 2 because our input frequency is 50 megahertz and we expected to get 100 megahertz of clock frequency. All right. So you can see this C0 is for 25 megahertz, C1 is for 10 megahertz, C2 is for 100 megahertz. So like this, you can select for C3 and C4. But for this project, we only wanted to have one clock output of 25 megahertz. So I will simply unclick this and I will simply unclick this C1 as well. So in this case, I will only have this C0 output of 25 megahertz, right? So now simply click on next, then next. So this is C3. Now this is C4. You can select these clock outputs from here as well. And once you have all these clock outputs configured, you can simply click on next button. Now I will leave this page as it is and then simply click on next. Now these are the couple of files that will be generated from this PLL. So you can see that these two options are grayed out, means these two files will be mandatory generated by this PLL, but you can select the file from these 4 files if you wanted to generate them or not. So for example, this CMP file, that is VHDL component declaration file, suppose I wanted to generate this and suppose I also wanted to generate this template file for component instantiation, right? So that it can save some of my time while instantiating our component into top level module project. All right. So you can simply tick this option as well, or you can leave also. Now, once you select all of these things, now simply click on this finish button. Now this is asking that if you wanted to add this PLL catalog or this IP catalog, or even we should say this module into our existing project or not. Now for this project, I wanted to add this IP into a project, right? So I will simply click on yes. Now if you notice at this file, so you can see that this is QIP file and that is generated in your IP folder that you have selected. So by mistake, if you forget to add this file into a project, you can also do that later as well. So just simply click on yes here in this window. Now, if you look at this hierarchy view, then you can only see the IP test here. We are not seeing the IP module here because we have just added that into a project, but we have not instantiated that in our top level project or top level module. So if you change the view from hierarchy to files here, now you will be able to see this QIP file and here you will see this clock pll.vsd project. So this is our IP, right? Now if you open this file, because this is a VHDL file, so you can see that how this PLL is created. So we have this library declaration, next we have this entity declaration, and finally we have this architecture declaration or architecture section. So you can see that this architecture section is quite long, all right? So these are all comments, but the main part is up to here. Okay. So this is our architecture section. Now, if you try to read this file, then you won't be able to see any logic about the division of clock frequency. Instead, this is a kind of a netlist that is generated by the Quartus Prime software. All right. You won't be able to see any logic about the clock division here, right? So that's our VHDL file and what we are really interested in this entity section, because we have to use this part to declare the component and to instantiate the component into our top level module. So what I will do that I will copy this part, that entity part from here, and now I will go to this IP test.vsg, which is our top level module. And now I will instantiate this component here in this top level module, right? So first we will declare this component. So this is a component here, and now this is AND component. Now I will copy this part to instantiate this in our program. Now first I will give the name of this component. Suppose this is clock PLL. All right. Now we do not need this is keyword from here. So I will remove this. Now the next section will be port map. So write port map. And now we will connect the ports of our components with our top level module ports or signals. So let's write the structure first. And we do not need this statement here for this component instantiation. So we have these three ports to interconnect with our top level module. So this asynchronous reset will be connected to a reset. So let's write it reset. Now this input clock 0 that will be connected to our main clock frequency or our system clock frequency. So that is clock here in our case. So this is clock, and this C0, so that is our output of our component. So that will be a 25 megahertz of clock frequency. And for this we will use one internal signal, and let's say the internal signal is clock underscore 25 megahertz, right? So this is the internal signal that is of clock of 25 megahertz. And this is our system clock frequency, and that is 50 megahertz. All right. So first we will define this clock signal, that is our internal signal. So I will define this. So that is signal clock 25 megahertz. Then that is std underscore logic type. All right. Okay, seems that I have mapped the component in the wrong section. So this will be coming here, and that part, that is component declaration, that will be going to this section. All right. Now this is good. No, that is not good. So what I will do that I will copy this part once again, and I will paste it here. And now replace this entity word with the component word. Same, I will copy this and paste it here. Now give the name of this component instantiation. So suppose this is clock PLL. Now we do not need this is keyword in the last. Now this will be port map, and now this looks good. All right. Now coming to the finite state machine, and now here we also need to change our clock signal. At the moment, this input clock, that is our 50 megahertz signal or 50 megahertz input, that is driving our finite state machine. But what we want, that we want to drive this with this 25 megahertz of clock frequency. So I will use this 25 megahertz of clock signal to drive this finite state machine, right? So I will replace this clock with the clock 25 megahertz. Now everything looks good. Now one more thing that I want to tell you, that this is one component instantiation of this PLL. Now if you wanted to use more clock signals, then you can also do this by the component instantiation. How? You can just simply copy this part from here. Now paste this. Now suppose this is clock PLL2, and now this time you wanted to have 12.5 megahertz of clock frequency to use in your project. And that is actually a half of 25 megahertz, right? And now what I will do, that I will connect this 25 megahertz of clock frequency to the another PLL as an input clock. And at the output, I would be getting a 12.5 megahertz, 12.5 megahertz, for example. So this is our another internal signal for 12.5 megahertz clock signal, right? This means that you can generate or you can instantiate as many clock signals as needed as per your requirements. All right. But here is a catch, because if you select the FPGA device that you are going to use in your project. So for example, if I select this hierarchy view from here, our device is this one, and this device only have two PLLs inside it. Means this is our first PLL and this is our second PLL. And both of these PLLs are now occupied by this project. This means that you are not able to use any third PLL in this project because the limitation of this device, because this device only have two PLLs inside it. So if you wanted to use more than one clock output, then better to select it from the IP Wizard itself. Like I demonstrated that you can select up to 5 clock outputs from that IP, right? But now for this program, we do not need this second PLL or second output clock frequency. So I will remove this section of code from here. Now the next step is compilation. So we will do the full compilation of this program. So I will click on this start compilation button. So you can see that it has been started and it can take up to 10-15 seconds. So you can see the process here or the progress here. So that is completed in 15 seconds and everything is good. All you can see in the green color, right? Means our VHDL code is free from any syntax error. And now we will give the pin planning to this module. So I will select this button. So I will click on this pin planner button. So you can see this is the top view of our FPGA device. So this is our side A, this is side B, this is side C, and this is side D. And this FPGA is having total 144 pins. And Quartus Prime software already identified all the input-output ports from our top level module. So you can see we have this clock as an input, reset as an input. We have 3 switches as an input, and these are LED 3 outputs. So what I will do here that I will select each port from our module and we will tell the Quartus Prime that this port is connected to which pin of this FPGA. Alright. So for example, this clock pin or this clock port is connected to the pin number 23. So you can see this pin is highlighted now and you can see that this clock input that is connected to the pin number 23. So that is mentioned, right? Now the next input is reset. Suppose this reset is connected to pin number 25. So I will give this pin number 25. Next we have 3 inputs for the switch input. So let's say these are connected to pin number 88. Now pin number 89. And this switch 3 is connected to pin number 90, right? Same, we have these 3 LED as an output. And let's say this is connected to pin number 85. Next is connected to 86 and next is connected to 87. So you can see that all the selected pins are highlighted in the FPGA top view here. Alright. Now note that these pin descriptions can be different for different boards and it depends on the FPGA board manufacturer. So you will be getting the specification sheet with your FPGA board and that will specify that which input or which peripheral is connected to the which port of your FPGA device. So you have to select your pins according to your FPGA manufacturer or the FPGA board manufacturer. Alright. Now you can see that all the input-output standards are selected by default to 2.5 volt. And for my FPGA board manufacturer, that is connected to the 3.3 volt. This means that I have to modify this 2.5 volt as per my FPGA board specification. Alright. So I will select this 3.3 volt LVTTL. Same for all the ports of this module. Okay, so that's done. Now because there is no save button in this window here, because pin planner automatically saves your configurations when you are making any changes to it. So you do not need to save anything here. You just simply click on this close button. And now because you have changed the configuration, so you need to recompile your program first. So simply click on this play button to start the compilation. Now while this is compiling our program, let's see that what files Quartus has generated for our IP component, right? So I will go to this IP test folder. So that is our project name. And here we are having the separate folder for our IP. Okay. So this is our folder. Simply open it. And here we have this PLL folder. Remember, we have created this folder for the clock PLL, right? So this is the benefit of creating a new folder for each IP component. So now here you can see that we have this clock PLL. So that is VHDL file. And that is the same file that I've shown you in the Quartus Prime software. I will show you this once again in a couple of seconds. Now this is the second file for the component instantiation. And we have generated this from the optional section, right? Now this is the main file, that is script file QIP. And if you wanted to use this PLL on some another project, then you can just simply import this QIP file and then this IP will be added to that project as well. Okay, so that is a quick brief. Now go back to the Quartus Prime software. So this is our clock PLL.vsd that I have shown you in the folder. Now, as I said, if you forget to add the IP into your project or you wanted to add any different IP into this project, then you can simply do this by selecting this FPGA device and now right click. Now go to settings and here you will see this files option and from here you can browse the file and then you can simply add that into this project. Alright. Now once you do this, we can open the programmer. So you can see the button here. We will simply click on this programmer button and this is the window will open to program your module into the FPGA device, right? So you can see that this is your FPGA device. This is the file name that will be written into your FPGA device. This is the name of your FPGA device. Now because this time our hardware is not connected, so I don't see any hardware is listed here. But in case you have connected it, then that hardware will be listed here. And even if after connecting your hardware is not displaying here, then simply click on this hardware setup and your device should be visible here in this box here. And if it is displayed, just select it and click on close. Okay. And after that, you will be able to see the hardware here in the section. And once your hardware is listed here and you select this programmer file, then you will see this start button will be popped up. So just simply click on start button and the progress of programming your module onto the FPGA will start from here. Okay, so that was a quick brief. Now because we have used the PLL and we have checked everything for this top level module, so now this is the time to review the netlist viewer and the fitter reports. And these are really important to understand this netlist viewer and the fitter reports when you are working on the Quartus Prime software and developing any project for your requirements. Okay, so let's close this programmer window. Okay, so that was our today's project. We learned a new concept of Quartus IP and we practiced a finite state machine too. We learned how to import a PLL IP in Quartus Prime, how to configure it, and how to use it in your designs. Now remember that the configuration of all the IPs listed in different categories can have different steps based on what it do. Like memory IPs will have different settings. Processors will have different settings like that. Now the next session is going to be interesting because in the next session, we will see the physical structure of this design. Means we will see that how different elements inside the FPGA are interconnected to meet today's requirement in real hardware. And we will use RTL viewer and technology map viewer for our designs. We will also see that how to navigate between these different elements in the netlist viewer. So stay tuned for the updates and I will see you in the next session.